All right, let's dive into this paper you've given us today.
Okay.
It's 2012.07805, extracting training data from large language models. And it's really tackling, I think, a question on a lot of people's minds these days, which is how much do these powerful LLMs actually memorize from their training data?
Yeah.
And we hear all the time about, these models are amazing, they can do all this stuff, and it doesn't seem like they're overfitting.
Right.
But is that really true?
Well, and that's what's so interesting about this paper, right? It really challenges that assumption
Yeah.
by demonstrating that extraction attacks on LLMs are not just theoretical, they're actually practical.
Okay.
Even on models like GPT-2 that show minimal overfitting.
Okay, so right off the bat, this is saying, like, GPT-2, we all think it's not overfitting.
Right.
But actually, we can get stuff out of it.
Yeah.
So for today's deep dive, we're specifically going to be looking at this paper, which analyzed GPT-2a 1.5 billion parameter model trained on a massive data set of publicly available internet data. So can you tell us a little bit about why they chose GPT-2 for this research?
Yeah, so the choice of GPT-2 is strategic for a few reasons.
Okay.
First, both the model and its training data are public,
Uh-huh.
which allows for ethical analysis and minimizes any potential real-world harm from the extraction process.
Okay, that makes sense. So we don't have to worry about, getting in trouble, essentially, by doing this.
Yeah, and also, we're not dealing with any kind of private data or sensitive information that we shouldn't have access to.
Right.
And it's a really clean and safe environment to conduct this kind of research.
Okay, and it's a well-studied model
Yeah.
that we can compare to other research.
Right. There's a lot of existing work on GPT-2, so it makes it easier to kind of contextualize the findings.
Yeah, makes sense.
Okay.
Okay, so before we get into, like, how they actually did this attack, let's kind of define what we mean by memorization in this context.
Right.
Because it's not like these models are, reciting verbatim lines of text.
Exactly. Yeah, you're right. It's not about sort of rote memorization like you might think of with like flashcards or something. The researchers here focus on what they call eidetic memorization.
Okay.
Which is the memorization of data that appears only a small number of times in the training set.
Okay.
And they use the variable k to denote this, where smaller k means stronger memorization.
Okay.
So think of it as a spectrum,
Okay.
right? The rarer a piece of information is in the training data, the more likely the model is to have sort of like really latched onto it and memorized it, and the greater the potential privacy concern becomes.
Interesting. So we're not just talking about, like, common phrases or patterns that you might see.
Right.
We're talking about potentially, like, unique information.
Yeah, potentially unique and sensitive information.
Sensitive information. Okay. So the researchers developed a two-step attack process to investigate this.
Yes.
Can you kind of walk us through how they actually went about extracting this memorized data?
Sure. So the first step is text generation. Right. They needed to get GPT-2 to produce diverse and interesting outputs.
Okay.
And they found that basic top-end sampling wasn't sufficient for this.
Because it would just give you the same thing over and over again.
Exactly.
Right.
It leads to repetitive and predictable text.
Right.
So instead, they employed two more advanced techniques.
Okay.
Sampling with a decaying temperature and conditioning the model with prefixes taken from independently scraped internet text.
Okay, so they essentially tricked GPT-2 into exploring more,
Exactly.
a wider range of possibilities, and behaving more like it would in a real-world scenario where it's presented with, a variety of prompts.
Yeah, that's a great way to put it.
Okay, that makes sense.
Right.
What about the second step?
Right.
How did they determine which of those generated outputs were actually memorized from the training data?
So that's where membership inference comes in.
Okay.
And the challenge here is to distinguish between text that is simply likely based on language patterns versus text that has been specifically memorized from the training data.
Yep.
Right. And they found that simply choosing high likelihood samples just leads to too many false positives.
I see. Okay.
So they needed a way to identify outputs that were unexpectedly likely, suggesting they had been memorized.
Okay. How did they go about doing that?
Well, they came up with a series of really clever techniques to pinpoint these unexpectedly high likelihood outputs.
Okay.
One approach involved comparing GPT-2's perplexity to the perplexity of smaller GPT-2 models.
Okay. Okay, so the idea is smaller models have less memory capacity.
Right.
So if a phrase is highly likely for the large GPT-2 but not for the smaller ones, that suggests memorization.
Exactly.
Right.
Yeah, it's like comparing, a vast library to a small bookshelf.
Okay.
The smaller model is less likely to have tucked away that specific piece of information.
Right. Okay. They also compared GPT-2's output to the output of zlib compression.
Right.
Wait, zlib compression?
Yeah.
That's the algorithm used to, like, zip files.
Is it?
What does that have to do with memorization?
They're like, it might seem strange, but it's a surprisingly effective baseline.
Okay.
So zlib is excellent at compressing repetitive sequences.
Yeah.
And LLMs sometimes get stuck repeating phrases or patterns.
Okay.
So if GPT-2 generates something highly repetitive, zlib will compress it very efficiently,
Okay.
indicating it's probably not a uniquely memorized piece of information.
Interesting. So they're essentially looking for instances where GPT-2 is behaving differently from these simpler systems,
Right.
suggesting it's drawing on memorized information. Were there any other techniques they used?
Yeah, they also compared the perplexity of a text with the perplexity of the same text after lowercasing it.
Okay.
And this is because capitalization is often a key indicator of memorization,
Okay.
especially for things like proper nouns, URLs, or code snippets.
Right.
So by seeing how the perplexity changes after lowercasing, they could detect if the model was sensitive to the specific capitalization patterns of the original text.
Clever. So if the perplexity drops significantly after lowercasing, it suggests the model has memorized the specific capitalization and formatting.
Exactly.
I can see how that would be a strong signal.
Yeah.
Okay. And finally, they analyzed the perplexity on a sliding window of 50 tokens.
Right.
This allowed them to detect memorized substrings within longer sequences that might otherwise have been missed.
Right.
It's like scanning a document for a specific phrase rather than just looking at the document as a whole.
Exactly.
Okay, with all these techniques in place, what kind of results did they find? Were they actually able to extract sensitive information from GPT-2?
The results were remarkable.
Okay.
They identified 604 unique memorized training examples out of 1,800 candidates they analyzed.
So like a third.
That's a true positive rate of over 33%. Yeah.
Wow, that's significant.
Yeah.
So what kind of information did they find?
They found a surprisingly diverse range of content.
Okay.
Everything from news headlines and code snippets to URLs and even personally identifiable information like names and contact info.
Wow. You can see all the details in Table 1 of the paper.
Okay, so this isn't just harmless trivia. They were able to extract information that could potentially be used to identify individuals or compromise their privacy.
Exactly.
Yeah.
Some of the findings were particularly concerning.
Okay, like what?
Well, they extracted 128-bit UIADs that appeared in only a few training documents.
Okay.
They were even able to correctly resolve URLs containing random substrings.
Oh, wow.
You know, the kind of information that's supposed to be difficult to guess.
That's unsettling. It highlights how sensitive information, even if publicly available, can be unintentionally memorized and potentially leaked by these models.
Precisely. And they even found instances where GPT-2 had memorized content that was no longer available online.
What?
Yeah.
So it's like the model became an unintentional archive
Exactly.
of deleted data.
Wow.
Yeah, it's pretty wild.
Okay. So out of all those different techniques, which ones were the most effective at identifying memorized content?
Well, conditioning the model with internet text yielded the most memorized content.
273 unique samples.
Okay.
And the comparison-based metrics for membership inference were far more effective than just looking at perplexity alone.
That makes sense. By mimicking real-world usage and looking for deviations from simpler models or baselines, they were able to zero in on the truly memorized content. Figure 3 in the paper really nicely illustrates how comparing zlib entropy to GPT-2 perplexity helps pinpoint these memorized examples. I encourage you to check it out. Now, I know the paper goes into detail about several specific examples of extracted data. Could you walk us through one that really highlights the potential impact of these findings?
Sure. One compelling example is the extraction of leaked Podesta emails from WikiLeaks.
Okay.
They found URLs from those emails memorized by GPT-2, even though they appeared in only one training document.
Wow, that's significant. It shows how even publicly available information can become a privacy risk if it's memorized by a model. Did the researchers explore how the size of the model affects its ability to memorize data?
Yes, and their findings raise another important concern.
They discovered that larger models tend to memorize significantly more data than smaller ones.
That's not entirely surprising, but it is concerning given the trend in AI research towards building larger and larger models.
Right.
How did they investigate this?
They used naturally occurring canaries in the training data to study this.
Okay.
Specifically, they looked at Reddit URLs that appeared a varying number of times in a single document.
Okay.
These URLs acted as markers, allowing them to track how often a specific piece of information needed to appear before it was memorized by different sized GPT-2 models.
Clever. So what did they find? How much repetition was needed to trigger memorization?
The largest GPT-2 model was able to memorize URLs that appeared 33 times or more in a single document.
Okay.
In contrast, the smallest GPT-2 model didn't memorize any of those URLs,
Okay.
even with additional context and a more powerful search strategy. The results are summarized in Table 4 of the paper.
So the larger the model, the more likely it is to memorize even relatively infrequent data points. This definitely has implications for the future of LLM development. But the big question is, what can we do about it? Did the researchers offer any solutions or mitigation strategies to prevent this kind of data leakage?
They discuss several potential strategies, each with its own strengths and limitations. It's an active area of research, so there's no silver bullet solution just yet.
Right.
But let's delve into some of the most promising approaches they highlighted.
Absolutely. I'm eager to hear what kind of defenses we might have against these extraction attacks.
So one promising approach they discussed is training with differential privacy.
Differential privacy.
Yeah.
I've heard that term before in the context of data security. Can you explain how it might apply to LLMs?
Sure. So differential privacy basically injects carefully calculated noise into the training data.
Okay.
And this noise makes it much harder to extract information about specific individuals or unique data points.
Okay.
It provides strong privacy guarantees, but it can impact the accuracy of the model and increase training time.
Right.
And scaling this to the massive data sets used for LLMs is a significant challenge.
So it's a powerful tool in theory,
Yeah.
but faces practical hurdles, especially when dealing with the scale of LLM training.
Right.
What other strategies did they propose?
Another key area is careful data curation.
Okay.
This involves meticulously filtering sensitive content from the training data set,
Okay.
rigorous deduplication, and sourcing data responsibly.
That sounds like common sense, but I imagine it's incredibly difficult to implement effectively, given the sheer volume of data we're talking about.
Absolutely. It requires robust systems and processes to identify and filter sensitive information at scale.
Yeah.
It's an ongoing challenge, but a crucial one if we want to mitigate privacy risks from the outset.
Right. So it's about minimizing the amount of sensitive information that even enters the training pipeline in the first place.
Exactly.
Okay. Are there ways to control how memorized information is used or accessed once the model is trained?
Yes, they discuss strategies for limiting the impact of memorization on downstream applications.
Okay.
For instance, fine-tuning an LLM for a specific task might actually cause it to forget some memorized information from pre-training.
Interesting. So the model's focus kind of shifts during fine-tuning,
Right.
and some of those old memories become less accessible.
Exactly. Of course, fine-tuning also presents new challenges.
Right.
If the fine-tuning data set itself contains sensitive information, we might introduce new leakage.
It's a delicate balance. It seems like we need safeguards at multiple stages of the process.
Yeah.
Did they discuss any strategies for preventing the model from revealing memorized information during its actual use?
Yes, they suggest filtering memorized content during application.
Okay.
Essentially, you'd have a system that monitors the model's output in real time and blocks the release of any potentially sensitive information that's been flagged as memorized.
So even if the model has memorized something, this safety net prevents it from being revealed.
Right.
How would we identify those memorized bits of information in real time, though?
Well, they propose adapting the same membership inference techniques they use for the extraction attack.
Okay.
Those comparisons to smaller models or zlib compression could be incorporated into the application itself.
So we're using the attacker's own playbook to defend against them.
Exactly. Yeah.
That's clever.
Yeah.
So we've got differential privacy, data curation, and these real-time safeguards during application.
Right.
Any other strategies worth mentioning?
The final strategy, and perhaps the most crucial, is auditing models for memorization.
Auditing makes sense.
Yeah.
It's like a quality control check to ensure that the mitigation strategies are actually working.
Precisely. Auditing involves empirically testing the model to see how much memorized information it can actually reveal.
Okay.
This helps us assess the effectiveness of our privacy measures and identify areas for improvement.
Yeah.
It's essential even when using differential privacy, as it provides a real-world assessment of the model's privacy guarantees.
So, to summarize, we have a multi-layered approach to addressing memorization in LLMs.
Right.
Differential privacy during training, meticulous data curation, safeguards during application, and rigorous auditing. It's a combination of preventative measures and real-time defenses.
Yes, and it's an active area of research.
Of course.
The ideal solution might involve a combination of these strategies or even entirely new approaches that haven't been explored yet.
This has been an incredibly insightful deep dive.
Yeah.
We've learned that memorization in LLMs is a real and pressing concern. Even models that don't exhibit overt overfitting can leak sensitive information. While there are promising mitigation strategies, it's an ongoing challenge that demands our attention.
I agree. This paper underscores the urgency of prioritizing data privacy as we develop increasingly powerful AI systems.
Right.
We need robust solutions that allow us to harness the capabilities of LLMs without compromising sensitive information.
Well said. For you listening, we encourage you to explore the full paper and the accompanying resources linked in the show notes. This is a complex issue with profound implications, and your insights are valuable as we navigate the evolving landscape of AI.
Absolutely. The future of responsible AI development relies on open discussion, critical analysis, and collaborative effort.
Thank you for joining us on this deep dive. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of knowledge responsibly.